The first speaker is Copetti, who works on all kinds of things, particularly generalized symmetries. He'll tell us about symmetries, defects, anomalies, and their constraints. Take it away.
Okay, thank you very much for the invitation. So I would clarify that the picture of the beach is not because it's November, it's a bit grim now. So like a picture of anomaly in flow. So I wanted the talk would be a bit about anomalies and how they can impact defect physics. And this is kind of, I don't know, to set the tone. Okay, so let's start with some introduction. So what are defects? So defects come in a variety of settings, and I will just sketch some of them, which for me are particularly important. Of course, I'm not talking about string theory here, which is important for many people here, so keep that in mind. So in QFT, you have Wilson lines in gauge theories. You can think about probes of symmetry breaking or confinement. This is another way to think about these localized defects, or people study a lot conformal defects, so defect in critical theories. I worked a bit on the physics of defects in amplitudes. So these are relevant for soliton scattering, especially in 1+1D. I already mentioned it's much harder to have definitive result. And you can think about scattering on confining strings or some type of strongly coupled objects. This is much less understood. And in condensed matter, also they come out in a lot of context. One is lattice impurities, which was one of the first instances in which defects were introduced, like the Kondo problem. Or you can think about performing local measurements on a quantum system. So you measure like a spin at some point. This is creating a defect. So if you are like wide enough with your definition, you can have defects in essentially every place you would like. So it's something that is very nice to study. But unfortunately, their dynamic is usually quite hard to understand because it tends to go to strong coupling. And even just classifying defects in conformal theory, which is a simple setting, 1+1D is an outstanding open problem. So I think the only theory in which they are completely classified is the 1+1D is in CFT. So this is this result by Affleck and Yoshikawa, and the partial classification in other settings, but it's extremely complicated problem. And of course, there are perturbative tools that one can use, like large N, epsilon expansion. You can use supersymmetry. But outside of these realms, very few exact results are known. So it's important to have new tools to understand like what can happen to different systems. And this is the idea of my talk. So an important part is played by symmetry, and symmetry is also described by defects. So topological defects are symmetry operations. And this just means that you can deform them freely. So this is just a picture of topological defect. And importantly, they interact with dynamical defect by giving them charges, which is usually talked about through this linking action. So for example, this would be 3D, a line defect, and this is a 1-4 symmetry defect, which can wind around. And when you shrink it, it gives you some charge. And the structure of these topological defects is encoded in higher fusion categories, which is just a complicated mathematical machinery. But actually, the important thing is that there is a lot of progress and a lot of new results in this kind of setting in the last few years. For example, the introduction of non-invertible symmetries. So there is a lot of things to import into physics from mathematics. But this symmetry action extended object is much richer than just this linking or giving charge to line operators. So I'll give you some simple example. If you talk about twist operators, so non-local operators which sit at the end of topological line, the symmetry action is encoded in this kind of picture, which is called the tube algebra. This is known. Very complicated object, but it's known. If you talk about boundary conditions, so symmetry acts on a system with a boundary, the correct notion is that the module category. So you can make your symmetry lines end on the boundary and changing the boundary condition. And if you talk about solitons and kings in 1+1D, you talk about this strip algebra. So now you should think of this as this Hilbert space on a very long interval, and the soliton has some boundary conditions for the field, which are A and B on the two sides. So it's interpolating between the two different values. And this is how the symmetry acts on the states in the Hilbert space of the soliton. This is also known structure, is very complicated, but now we have some good understanding of the important pieces. And there is much more. So this is just 1+1D. And in higher dimension, there is much more to be understood or studied. And usually these are called maybe higher representation, higher charges. And to be very general, we can just say these are describing how a defect can couple to bulk symmetry. This is what you want to know. And it's an important concept if you want to use symmetry as a constraining power for defects. And it's interesting that this realization can be very non-trivial. So one thing that was realized quite recently is that bulk symmetry can be realized in an anomalous way on the defect. This leads to the notion of defect anomaly. It's a symmetry which has not of the anomaly in the bulk, but it has an anomaly localized in the defect. And so what I want to do is understand how these high representations can impose constraints on defect physics and fix some interesting observables exactly. So just put it in clear terms. So what are the aims? So provide universal and exact constraints. So universal because it don't depend really on the type of bulk systems you have, but just on the symmetry structure. And exact because the symmetry data are exact and are invariant. So these things you compute in the UV at weak coupling and they're remaining there. So it's very important with respect to toolbative tools. And you can try to classify defects. And one thing that we try to do all the time is find interesting RG invariants that are associated to symmetry action, match them to give some constraints on IR of defect systems. And the other part is more applied. So if you know symmetry acts, you can inform numerical methods like bootstrap. We did this for the S-matrix bootstrap in this work. And there's a very nice, there are two, I think, very natural avenues. One is a solitons in adjoint QCD2. This is just a picture of the backbone in adjoint QCD2. These are the solitons. There is some interesting symmetry here, and the S-matrix of this is unknown. It's a very natural theory for quantum simulations, but very little is known about these solitons. And the one is for like conformal bootstrap. There is a recent paper that talked about using the defect ending or defect changing operators in the bootstrap program. It's actually quite interesting for getting positivity in the defect bootstrap. They usually don't have. But the symmetry action, this type of operator is really interesting. It's not very well understood. This is like a nice way in which you could apply symmetry to numerical methods. And there have been like a lot of results already. Like I started working on this last year, and I think there was not so much done from the perspective of generalized symmetries before. And there is already a lot of interesting stuff coming out. So first, last year, people discussed symmetry-breaking defects and their conformal manifold in many works. These higher charges and their formulation was pioneered in these two papers, and I did some work on this. This concept of defect anomalies and how they can can be matched in the IR and then can give rise to interesting dualities between defects was explained in our paper in December, and then this paper by Zohar very recently. You can also find the no-go theorems for screening of lattice impurities by just using symmetry constraints. So you can say that symmetry can avoid bulk screening of a defect. This we also did last year. We had nice results on scattering amplitudes, especially modification of crossing symmetry and the bootstrap in the presence of non-invertible symmetry. This was two works last year with Shota and Lucia. We talked about how defect system can have extended symmetry, so they can have more symmetries than the bulk system, which led to this notion of sub-phantom symmetry you can use to constrain some observables of defects, like the reflection coefficient. There are interesting proposals for monopole scattering, so what's called the Kalna-Lubakov effect, in this paper 2 years ago of David and the collaborators. And I have some work in progress about how you can use defect anomalies to explain all these interesting effects. And what I will talk about today is some interesting interplay between bulk anomalies and the topology of symmetry-breaking defects. So it's about how you knowing how the bulk system acts on bulk symmetry acts on trivially can tell you something deep about boundary condition defects in the theory, which is exact. And there is also some parallel work by Yichul Choi and collaborators about this, and some work in condensed matter context. So there's a lot of going on in this. And this will be like a very self-contained application because the talk is short, and I wanted to have something that people could just really appreciate in 10 minutes. So first, we consider what is a symmetry-breaking defect. So if you have a G-symmetry, continuous symmetry, just think of U1 for this talk. You have a conserved current, but in the presence of a defect, this can be broken by a contactor, which we call the tilt operator. So when this is non-trivial operator, meaning not total derivative, the defect breaks the symmetry. Okay, this is the characterization in QFT of symmetry breaking. And if you break a continuous symmetry, you define a continuous family of defects, which are called d sigma. D is a defect, sigma is the parameter in EU1, which you can think of it as the action of the bulk symmetry on the symmetry breaking defect. Or alternative, you can turn on a perturbation on the defect, given by a trace of sigma times the tilt operator. And this is like topological picture. So defect ends and the topological defect for the symmetry ends, and the defect changes along the time direction.
Why do you call it tilt?
Usually people introduce this in the OM model, and then in the OM model you put just the pi field. I don't know what's the question. Okay, and yeah, I think it's just you put some vector value. It's just for an example in the OM model. It's not like a deep name, but this is the name that's stuck around in the literature because the first examples were in the OM model. Okay, so that's what I know at least. Okay, so we also introduce anomalies. So if we consider bulk symmetries which are anomalous. So it just means that the partition function transforms as a section of a line bundle under gauge transformation, like triangle anomalies in 4D. This is what I'm talking about today. And these are classified by solutions to the Vezzo-Mino consistency conditions, which are these equations. And non-trivial solutions are distinguished by an integer coefficient, which I call chi. The chi will be the anomaly coefficient. This will appear later, and this will appear later. But this is well-known stuff from the 60s to the 80s, I would say. And an interesting observation is that if the anomaly is non-trivial, the boundary conditions for the theory must break the symmetry. So this is something that was proven in this paper in a more restricted scenario and more recently by Totten and Wang. So it's an interesting observation, and we call this anomaly enforced. So there is, if you have an anomaly in a bulk symmetry, you cannot preserve the symmetry on the boundary. And a natural question is that if this type of symmetry breaking is different from just, putting a symmetry breaking boundary condition for the OM model while the field points in some direction. And how is the boundary physics sensible to the bulk anomaly? So where do you see this? So there are two ways to approach the problem. One is to consider correlation functions. That's what people would do in the CFT. And the other one, which also works for non-conformal system, is to couple the system to a background gauge. And at first sight, it might seem impossible to do so, because if you just naively couple the background, you use the conservation equations before, you see that you get the boundary term, which is proportional to the tilt operator. So the system is not gauge invariant. And this is just symmetry breaking, of course, it's not something deep. Go around this by considering the dependence of a modulated symmetry breaking parameter. So this was the U1 parameter. Now we make it space-time dependent. This is what you always do when you have some symmetry which is spontaneously broken. No, this would be a bit like a Goldstone field. And now the gauge symmetry is there, but is realized non-linearly on the sigma field. So now you can couple the symmetry breaking defect to the gauge field. It's a nice setup, and I will denote the modulated defect, this wiggly line. And now we can construct the effective action. So we just take the partition function with the defect divided by the one without the defect, and we construct the effective action. We depend on the bulk gauge field and the symmetry breaking parameter. So now we try to see whether the anomaly fixes some universal terms in FB. And this is actually easy to see. So if you have a manifold with boundary and you consider the Vezzo-Mino consistency condition, you will get a boundary term usually. And it turns out that you cannot cancel this by local counterterms on the boundary, just using the gauge field. This was the origin of this paper. But you can do so if you consider the modulated parameter sigma. So in this presence, you get this kind of equation, which is where the Vezzo-Mino consistency condition lies, so just the commutativity of gauge transformations. And you can trivialize this boundary term if you can find the boundary functional which transforms in this way, which is a very simple condition. So you put this condition in and you compute, which is what I did. So example is U1 anomalies. So these are the anomalies in 1 + 1D and 3 + 1D. Usually you see them integrated by parts, but this is the most convenient form for me. And you solve these equations and you find the effective action. So you see there is this term. It looks a bit like Chern-Simons term in 1D, and then there is corrections in the derivative of the field, and here is the same. is proportional to the anomaly coefficient. So the anomaly is not there, you don't get this term, but it's an integer, it's an exact result. You just compute the weak coupling, whatever system is correct, and it's exact. And then dots are higher derivative corrections that I'm not talking about here. So this is something you can do in one line. You can do also for all G's. This is just U1. And this has striking consequences for the boundary physics, because now you can take derivatives of this effective action, and you find that there are some currents, like quantum pole currents, which lie on the boundary. These are exact in the sense that they are just fixed by the anomaly in the symmetry-breaking parameter. These are exact if you compute them in one loop. You can put any order is an exact result. And I mean, an integer current you can always remove by stacking a quantum pole state on the boundary. So this sigma just takes value in 0 from 2 pi, and if you move by 2 pi, you can redefine the system a bit and remove the current. But the fractional part is there, it's physical and is exact as a consequence of the anomaly. And an open question is, what is the experimental relevance of this current? So you can realize these things in like QCD scenarios. You can realize this in QED. So can we measure this stuff? Can we measure this in the lab? I don't know, but it's an interesting question. And from a point of view of topology, there's an alternative way of thinking about this effect, which is we take this sigma parameter and we go around this circle. This is the U1 parameter, you go around. And when you go around, the system doesn't go back to itself. It goes back to itself times stacking of a SPT for U1. This is the SPT, since I'm still with integer level. And this is just a quantum pole state, integer quantum pole state. So when you have the anomaly, you go around this circle, you just turn on the symmetry-breaking parameter bit by bit, you go around 2 pi, and you create this non-trivial order state on the boundary. And this signals there is some kind of non-trivial topology of this conformal manifold for the defect, and this fixed by the bulk anomaly. This is like some very, I don't know, interesting idea that you can have. And these people study this in condensed matter more in a different context, and there are other nice ways to derive it. So just quick example, free scalar 1 plus 1D. This is anomaly for the U1 momentum times U1 winding symmetry is this one, very well known. Boundary condition, Dirichlet preserves the winding, Neumann preserves the momentum, so we choose Neumann. You can choose Dirichlet, it's the same. And to describe Neumann with some symmetry-breaking parameter beta is the same of sigma beta. You just put on a theta term on the boundary. This is the action. So now you couple the scalar to the gauge field for the momentum symmetry. This is the coupling, and you find this term in the boundary effective action, which was the linear term I told you before. So you can also derive it in examples very easily. You can do the same in 3 plus 1D for the fermion by turning on the mass in half space with some phase. I will not talk about it here because it's a bit too long, but there are nice ways to derive this to check the results. So just for the outlook. So I wanted to show there is some deep interplay between bulk Toft anomaly and the topology and transport properties of defects. What is nice to do? So you can translate these constraints into conformal data and some rules. For Abelian groups, there are some things you can do. I didn't do it in the paper, but I'm sure you can do it. Interesting thing is you can gauge the symmetry. So you can talk about QED and QCD, and then this A will be a dynamical gauge field. I don't know like what is happening on the Neumann boundary condition, but seems very interesting. Another point is higher invariance. So today we had the circle and we looked at the pi 1. We got around the circle once. What about the homotopy groups of the defect families? Can we also see this from bulk anomalies? Are they similar into place? Another interesting work in progress is to do this for twist defects. So if you consider now monogamy defect is also called, so just terminating a topological line in the bulk, you turn on the anomaly. And you can actually see that this type of reasoning also gives you very interesting universal constraints on the spectrum on these twist defects. And this is kind of work in progress. I thought about this last week, so I need like 1 month to finish it. But, but it's very interesting, and it works in a similar way, and it's something that, as far as I know, is unknown. Okay.
Hey, question. Thanks for a nice talk. Okay, let me ask a question. You looked at U1. Can you say a bit more about when I think the topology of U1 was quite important?
Yeah.
So when you have other groups, when you don't have one cycles, for
You
example.
don't have one cycle, so you don't pump an SPT
Yeah,
when you
so-
go around. But you still have this some kind of hold response. It's just that there is no way to think of it as topological pumping around. But it's also there's also some non-trivial cases I didn't talk about here, in which the coefficients are not quite quantized in the right way, so you get some non-invertible topological order, I think. But I didn't look at it in the paper. I mean, there's a lot to do actually, but okay, this was just the beginning of this kind of ideas.
So I think the normal anomaly story, you can fix the higher ordered terms in the inflow from the Weissman conditions. Here you left it as a ... Is there a similar story?
No, I mean, it's all fixed. It's just a bit ugly.
Okay.
For U1, there is nothing but ...
Yeah.
For the non-abelian group, you can also do it for this boundary stuff. But then there is also parts of the effective action which are non-universal, and these I don't talk about. It's not doesn't come from the anomaly.
Thank you.
Is there anything more you can say about the quantum Hall slide that you were?
Well, I mean,
you mentioned something about experimental implications. Is there anything further to that, or?
I mean, the problem is just finding a good experimental setup. So,
What would that be?
I mean, if you just take like a 3D Dirac system in 3+1D, you put a boundary to it. The prediction is that if you put the axial symmetry-breaking boundaries, the usual boundary conditions, and you turn on this very slowly, you will get this full effect. Another way to see it is that you can turn on the mass for the Dirac terminal space. Here, this doesn't work. Well, you turn on this one. Something will. Let's try. I mean, this is for those who come after, no? So you turn on a mass like this in our space, a big mass, this gaseous system, but you get some non-trivial topological response for this. And this is what creates the quantum Hall state on the boundary. So if you go around here, you will pump one quantum Hall state from here. This I think you can do it, but this with the right fermions, this is not deformation. It's a bit small, maybe for the.
No, but it's also invisible.
It can be. Is the right factor? I don't know. I think it's the same, no?
M.
It's M. I mean, it's a fermion mass in our state, so this is pretty standard.
Okay. Any other questions? Where? Okay.
Sorry, I know you said you haven't thought about this much yet, but I'm curious about the monodromy defects bit. What kind of constraints do you
I can tell you, yeah, I can tell you for there. I hope like the black is the only one, but let's continue trying. So the red was better. Yeah. Okay, good. For me, it's the same, so I don't really see the difference. Good. So no, that's not no. Let's try another one. Yeah. Okay, this would be a monodromy defect, and this would be a defect, and you go around them, say e to the I alpha, no? So U1 defect. And you have a Toft anomaly. So if you have a Toft anomaly, the background gauge field is not flat. No, so the problem of talking about defects, like not boundaries, is that you have to turn on the anomaly, and usually you don't. You have in SUSY you do because you can put U1R kind of backgrounds, but in non-SUSY you don't, and this is not the way to do it. No? And what you get, well, there are two sets. People study this in 1D, these defects like this. And it's known that when you have an anomaly, you get some projective.
Sorry, by 1D you mean line defect?
1D,
yeah.
This is to DCFT, for example. And here you know the symmetry action is some interesting projective representation. This you can derive easily. But you can do 3+1D surface defects. And then you will discover there is a chiral sector which is protected. So it's a bit like fractional quantum Hall system that has a boundary. And the boundary of fractional quantum Hall system is some chiral CFT. And the kind of chiral data, which are there too, there is the whole conductance nu, and with the C minus, the thermal conductance. This you can read from the bulk anomalies of the system. There's a gravitational anomaly with a U anomaly. This you can read off, and then so you can say what's happening there. And yeah, I have just to do the computation in the free theory just to show it. I mean, it's obviously it works, but you can do the computation with the 3D rack and do axial twist. This is something you can do. I mean, it's a bit of an ugly equation. You have to solve the data operator in some nice background, but it's okay within the realm of that techniques. So, but this is works also to interacting theory. It's just a sector which is protected by the anomaly.
Sure.
Okay.
Okay, thank you.
All right, I have a small question. So,
Wait.
oh, sorry.
I mean, just a follow up about this quantum Hall thing. So, maybe you can try to like make a system, a 4K system, like maybe make this like sigma like periodic, has some like periodic dependence, and then you can ask like where there's some new boundary phenomena from in this 4K system.
Yeah, I think that's a natural. I think people thought about it in CondMath. So there's a paper by Ryan Thorngren, and there is another paper that I don't remember the authors. But I think people thought about this in this from this perspective. Yeah, so you're right. Like this is a very natural thing to do. So that's what we want to try. That's also the experimental set. I would say.
Well, I mean, I guess if you want to do experiment, that's typically what we want to do. Yeah.
Yeah, absolutely. So for high energy, would usually think about free fermion theories or something like this, but maybe CondMath is more rich, I think, for like applications.
And I think we thank Christian again for something.